In this video, we will study the Heisenberg uncertainty principle. In order to understand this principle, we need to be clear that the position and momentum are the most basic magnitudes necessary to describe a system. We know from classical physics that the position and momentum of large-scale and human-scale objects are perfectly defined simultaneously. Actually, it is clear that up to the size of small insects, the simultaneity of position and momentum can be achieved. However, when the scale of objects goes below 50 nanometers, the quantum effects start becoming apparent. Then molecules, atoms, electrons, and smaller entities are subject to the quantum regime. Now, let's focus on the Heisenberg uncertainty principle. This principle was proposed by Werner Heisenberg in 1927 as an important contribution to the quantum mechanics, and stating that the speed and the position of a quantum system cannot be determined simultaneously. In order to understand this principle, let's think of the following idea. Let's suppose that we have a function called f of x. This function can have any shape, but for the purpose of this example, we assume it is a Gaussian function. Now let's calculate the Fourier transform of the function and show both in the same graph, where the black line represents the function, while the red one is the Fourier transform. If now we change the width of the function by modifying sigma, then we can see that the Fourier transform is spreading as the function localizes, and vice versa. A natural question is the following: how is the Fourier transform related to the uncertainty principle? Actually, the answer is quite simple. The Fourier transform returns the spatial frequencies of the analyzed function. For example, if the function is a sine function with spatial frequency of 1, then Fourier transform shows a single peak at k equal to 1. On the other hand, we know that by definition, the spatial frequency of a periodic function is also known as the wave number, defined as follows. But the wave number is also related to the momentum, as stated by the de Broglie theory. Then, we can conclude that the spatial frequency is a different form of the momentum. This means that the Fourier transform determines the momentum or momenta carried by a wave function. We can conclude that in our previous analysis, if the function f of x was the position, then the Fourier transform is the momenta. Finally, we see that if the localization decreases, then the momentum is well defined, and vice versa. Formally, the Heisenberg principle states that the position and momentum cannot be simultaneously measured up to an infinite precision. In other words, the product of the uncertainty of the position and momentum is always larger than half of the reduced Planck's constant. Let's solve an example to understand in a better way the uncertainty principle. Example 21. An electron moves along a straight path with a speed of 4 million meters per second, with an uncertainty of 1%. Calculate the uncertainty in the position of the electron. Could you solve it? Answer. We see that the speed is much smaller than the speed of light, then we can use the classical momentum formula. Also, the uncertainty in the measurement of the speed is 1%. Then, the uncertainty in the speed is the following. We use the classical definition of the momentum to find the uncertainty on it. In this sense, we can calculate the momentum uncertainty by using the fact that the mass of the electron is constant. then the uncertainty in the momentum is simply this. Using the Heisenberg uncertainty principle, we see that the uncertainty in the position can be calculated as follows. Finally, the uncertainty is simply. We can see how the uncertainty in the position of the electron is very big, if we compare it with the size of an atom. This is due to the large uncertainty at which the speed of the electron was measured. In the next videos, we will keep exploring the quantum theory. Stay tuned.